Now it's time to look at Pascal's principle. And Pascal's principle relates pressures of incompressible fluids. All right, so suppose I have a cylindrical container and it has a movable piston. Okay. And suppose that um, there's an incompressible fluid inside. Okay. So what we mean by incompressible is not like Play-Doh, right? You can take a wad of Play-Doh and you can roll it around and you can compress it down into a smaller volume. Um, Now you can take incompressible fluids and you can take it to a smaller volume, but it exerts more pressure as you do. Okay, so uh, if we have the Play-Doh doesn't. That's the thought there. Okay, so um, if we have pressure being exerted everywhere, by the fluid, now this pressure is going to be uniform. Okay, so and this is just a balancing forces issue. Okay, if the pressure weren't the same everywhere inside the container, then the fluid would not be in equilibrium and it would flow from one part of the container to the other until the forces did balance. Okay, so what's going to happen now if I take the piston and I push it down? Okay, so its original level was right here, and I push it down to right here, for example, say. So I've exerted a much larger force. Okay, so I'm going to call this F push. And let's call this scenario F1. So F1 is the pressure force on the piston. In initial scenario. Okay. And if I take my piston and I push it down some distance delta y or h, whatever you would like to call it, okay, I have changed the volume with which the fluid can exist, right? So originally, the volume here would be my area A times this height h1. And so now this height h2, okay? So my initial volume was A times h1. My second volume is A times h2. And h1 equals h2 plus delta y. All right, so our volumes are going to be different by this amount. And so when you do this to an incompressible fluid, the fluid has to exert larger forces outward, and so the pressure increases. Everywhere in the container. So Pascal's principle basically says that any change in pressure in a container with an incompressible fluid transfers that pressure, that change in pressure, everywhere in the container. Okay, so Pascal's principle uh, basically says that everywhere in the container experiences the same delta P. Um, so this is F2. Uh, Actually, I wanted this to be P. I want this to be P. This is pressure 1. Now, we could find F1 if we knew the total surface area with which the pressure was exerting forces, but we're really actually interested in the pressure. So ignore this F1 here. It's fine. But what we're really interested in is this change in pressure. Okay. And so Pascal's principle says that this change in pressure occurs everywhere in the container. Okay. So there is a very severe consequence with this. All right. Um, and that consequence is, well, first things first, uh, if we look at this first situation, okay, so obviously if the piston is equilibrium, then you have the weight of the piston, okay, and the weight of the piston must be balanced by the force from the pressure. And so this is going to be F1A. And over here, you have the weight of the piston plus the pushing force. So the weight of the piston plus the pushing force must equal this new change in pressure, or not the change in pressure, but the new pressure, P2 times our area. But P2 is equal to delta P plus P1. So our weight plus the pushing force must equal delta P plus P1 times A. And since our weight is equal to F1 times A, this is going to be delta P times A plus P1A, which is delta PA plus F1. So our weight cancels out with the original force that was there, and our pushing force is equal to this change in pressure times the area. Okay, so whatever pushing force you exert down is going to be equal to the change in pressure inside your container times the surface area over which the fluid is exerting forces. Okay? Now, so to kind of take this to the next level, right? Consider a container with two pistons. Let me actually draw it this way. This is crude, but you kind of get the idea, hopefully. Well, you hopefully will get the idea here in a moment. Okay? So imagine I have a piston here that I can move, and imagine that I have a piston here that I can move. Okay? And inside here is an incompressible fluid. And what's going to happen if I exert a downward force on this particular piston? Now, from this slide, okay, we can see that the pushing force, I don't care what the original pressure was. All I'm concerned with is the change in pressure. Okay, all I'm concerned with is the change in pressure that will occur everywhere, right? And so, if I push down on this piston such that it, you know, comes down maybe to here, and so I have a delta Y here, then there will be a delta P. So these arrows represent delta P. And they really all should be the same length. If I get some longer than others, forgive me, but this delta P is going to be constant everywhere against every surface. So it'll be easier to kind of lengthen some of these that are shorter than it will be to erase the whole thing and start over. Okay. So imagine that everywhere has the exact same delta P. Well, with that extra delta P, if my second piston, if I label this piston 1, and I label, I really shouldn't use P. This is piston 2, okay? Then if the original piston 2 was in equilibrium, then the original pressure from the fluid was counterbalancing its weight. And so this increase in pressure, this delta P, will actually cause an upward force. Maybe we should call it F lift, if you will. Okay? And so, if I want to look at these forces, Fp for my pushing force is equal to my change in pressure times area 1. And so piston 1 has area 1. Piston 2 will have area 2. But F lift will have delta P times A2. Okay? So notice these forces don't have to be the same. If these are equal, but these are not equal, then these will not be equal. Okay? So my pushing force and my lifting force do not have to be equal. And my areas don't have to be equal. Okay? So, what this means though is, if I take the ratio of these, the ratio of my pushing force to my lifting force is equal to the change in pressure times area 1 over the change in pressure times area 2. but my changes in pressures are the same everywhere from Pascal's principle. The change in pressure occurs everywhere where the fluid is. And so my pushing force is equal to my lifting force, or the ratio of my pushing force to my lifting force is equal to the ratio of the areas. Okay? So what this means is if I actually want to lift something with this piston, okay, if I want to lift something with this piston, I can calculate what force is necessary by solving this ratio, right? Cross multiply and do your division. So my lifting force is going to be equal to my pushing force times the ratio of area 2 to area 1. And as you can see, if area 2 is larger than area 1, this will be an increase in force. Okay? This will be an increase in force. So, for example, let's suppose that area 1, I don't know, might have an area of 0.1 meters squared. And area 2, let's be extreme. Let's let it have 2 square meters. And let's let F1 be a downward force of 50 newtons. What will the lifting force be? Okay. So from the previous equation, we have the F lift is equal to the pushing force times the ratio of A2 to A1. So this is 50 newtons times 2.0 square meters divided by 0.1 square meters. And so this is a factor of 20. So 20 times 50 is 1,000. So in principle, I can lift an object of 1,000 newtons in weight with this hydraulic press. Okay, this is the idea behind hydraulic lifts. So if you've ever had your car worked on with a hydraulic lift, this is the working principle behind that. Okay? So now, in a true hydraulic lift, this is much smaller, right? By far. But in any case, right, this is the basic idea. And so you can lift things with far larger weights than what you're able to exert on that object if you can build a hydraulic lift. All you have to do is push down on a really, really small cylinder into an incompressible fluid, and that incompressible fluid will transfer the change in pressure everywhere. And because that pressure is going to be exerted over a much larger area on the other side with the other lift, or the other cylinder, piston, if you will, then the total force that you're lifting it with must be larger. Okay? But there's a catch. So what is the catch? Energy is still conserved. So that means the work done by the pushing force must be equal to the work done by the lifting force. Okay? And so what we can say is our pushing force times the, I used delta y, didn't I? Yeah. So in this case, we need to use delta y. So this piston is going to lift some amount delta y2 Okay. And these works have to be equal. So you can't get anything for free, right? Whatever work you put into pushing the first piston down, that will be equal to the work you get with your second piston. So let's even just say that this is 1 meter, okay? So my pushing force is 50 newtons, and I push it down 1 meter, okay? And my lifting force is 1,000 newtons. And what will delta y be? Okay, so delta y 2, by the way, is going to be 50 times 1, or 50 times 1 divided by 1,000. Okay, and this ratio actually turns out to be the same ratio as the ratio of the areas, right? So 50 divided by 1,000 is 1/20th, right? And area 1 to area 2 is equal to 1/20th in this case, or 0.05. Okay, so I'm going to be able to lift, even though I increase the force 20 times, the lifting distance is going to be 20 times less, right? So this is 1/20th times 1 meter, or 0.05, or 5 centimeters. Okay, so with this particular setup, even though you can lift 1,000 newtons, you can raise 1,000 newtons, you're not going to lift it very far, even by pushing your original cylinder down quite a ways, right? So in reality, most modern hydraulic lifts, this area A1, you want to be as small as possible. Okay, and that allows whatever forces are then exerting down on the pistons uh, to exert as large forces as they can on the second cylinder. And then one of the other major considerations is you want the tube that this piston can be in to be very long. Okay. So that allows, if you can keep pushing that first piston down and down and down and down and down, of course, the longer you make delta y1, okay, since delta y2 is proportional to delta y1, the longer you can push down delta y1, or the further, I should say, then the further you can push uh, delta y2 up, right? So that is Pascal's principle with a short application example. So the next video is going to be Archimedes' principle and Bernoulli's principle, and we will see you then.